able to do that, but if you can, it's fine, or I can try
No,
again.
Sir,
it
it
doesn't.
started.
Oh,
Ma'am,
it
it
started.
started.
Yes.
Oh, it started. Great.
Mhm.
Okay,
Great.
so we can start. Okay. Just give me 1 second. I mean, people are joining, so I have to admit them, and I'm the only one who can do that. This is a difficulty with the Google Meet. They don't allow anyone else to do it. Okay, so good evening, all of you, or good morning, Malabika, and good day to everyone who is here for a special colloquium today. And our esteemed speaker today is Professor Malabika Pramanik. And the title of our talk is, So You Think You Can Solve X plus Y equal to 2Z. And of course, Professor Malabika Pramanik really does not need any introduction, but it's always good. We all feel excited to share her accomplishments. So I'll just read a few things. So Professor Malabika Pramanik is a professor of mathematics at the University of British Columbia in Vancouver, Canada. She received her bachelor's and master's in statistics from the Indian Statistical Institute, and she did her PhD in math from University of California at Berkeley. Before joining UBC in 2006, Malabika held several postdoctoral positions at the University of Wisconsin, University of Rochester, and California Institute of Technology. She works in harmonic analysis and is especially interested in its interface with geometric measure theory, additive combinatorics, partial differential equations, and several complex variables. Malabika's research and teaching have been recognized through various awards and honors, among them UBC's Killam Research Award and Teaching Award Ruth E. Mishler Memorial Prize, and the prestigious Canadian Mathematical Society's Krieger Nelson Prize for Research Excellence. She is an inaugural fellow of the CMS and an invited speaker at the 2022 ICM. Since 2020, she has been the scientific director of Banff International Research Center. And I have to say, being in STEM, we all know that the journey as a woman scientist, as a woman mathematician is not particularly easy. It's quite rough. So we can confidently say that Malabika has broken many glass ceilings. And she is an inspiration to everyone. But I have to say in particular, so many aspiring young women students of mathematics, researchers of mathematics, wrote to me, felt very excited and eager to see her talk. That's really particularly exciting for me also. She is your role model, folks. And you can dream looking at her. And I'm eternally grateful to Malabika because she has taken her time out from her busy schedule to be with us this evening. So I shouldn't waste any more words. Over to you, Malabika.
Thank you, Sudeshna, for the wonderful introduction. I feel really privileged and humbled by your kind words. Thank you very much to the colloquium committee of RKMVERI for the opportunity to be here with you today. It's one of the most enjoyable parts of my job when I get to talk with the bright young minds, the upcoming STEM workforce who are going to shape our discipline in the years to come. So it's a privilege to share the little things that I know with you. Okay, so the title, I'm going to try and share my screen and see if everything works out. So are you able to?
Yeah, I can see your screen.
And is the whiteboard fully visible?
Yes, it is.
Okay, excellent. So the plan is I'm going to start writing, and during the check, I think there is a little bit of a lag between my writing and your seeing it. So I will make frequent stops to make sure that you are following. And please do write on the chat window. Sudeshna promised that she would keep an eye on it and let me know as questions arise. What I want to talk about today is a circle of ideas that I have been very intrigued by for many years now. And I'm going to pick a small prototype of this genre of problems and try to share with you today why it's one of those proverbial problems which don't seem to let you go. To me, at least, for a number of reasons. Okay. So let me start with some basics, and we will move up from there. All right, so we are going to, for the most part in this talk, going to be concerned with this equation x plus y equals 2z, but this is really just an example of a much bigger class of problems. So what do we know? All right, so suppose we have 3 points x, y, and z on the real line, satisfying this equation that I call star. What does it mean? Well, it means a few things. So suppose that there are these 2 points x and y, and then z is the midpoint of the two. And from our high school linear algebra, what we know is that star is a homogeneous linear equation which is linear in 3 variables. And the variables are, of course, the unknowns are x, y, and z. Now, whenever this happens...
Sorry, Malabika, can I just interrupt a little bit? Can everyone see the screen? Because I'm just seeing a very small portion.
I can see.
I can see.
Okay, good. Then it's my problem. So, Malabika, you can continue. Thank you.
Okay, great. So right now, the rightmost part on my screen is the x, y, and z, and you can see it, right?
Yes.
Okay, good.
Yes, ma'am.
All right. So this is an example of what is called an underdetermined system. So what does that mean? So underdetermined system. And so underdetermined means that there are more variables than equations. So in other words, more unknowns than equations. And very early on, we are told that every time you are in a scenario where there are more unknowns than equation, it's a great situation to be in. What one can do, so we can can choose x and y arbitrarily, And if we do so, then Z is determined by the equation star. Okay. So that means that we have an infinite family of equations parameterized by two independent parameters. So the solution set is infinite parameterized by X and Y arbitrary in R. Okay, so this is what we understand. Now, today's talk is really going to provide a counterpoint to this particular piece of wisdom that we gathered very early on. What I'm trying to get at is that certain things are sort of surreptitiously brushed under the rug when we solve equations in the reals. And we want to sort of take a critical look at what it means by solving equations in a certain set. Okay, now let's see. Let's start with a particular, so how do I do this? Let's make a definition. So my question is, but is X plus Y equals to Z always solvable? Okay. All right. Now, in order to make a sort of strong case out of this, maybe we should start with a definition of when we say an equation is solvable or not in a set. So here's our first definition. So suppose you choose any set capital E. And for this talk, at least, let's just restrict to things that we know, the real line or the integers. So one is the real line is it's an example of a set in the continuum. Otherwise, in Z, it's discrete. We are going to say that E contains a non-trivial solution of X plus Y equals to Z if there exist 3 points X, Y, and Z contained inside of E, all 3 points. And that, of course, there are trivial solutions. If you take any X and then you set Y and Z to be the same as X, of course, this equation is always satisfied, but that's no good. We want these 3 points to be distinct. X has to be strictly less than Z, and Z has to be strictly less than Y, and this triplet has to obey the equation star. Now, if no such triple exists, then we say that E avoids star. If no non-trivial solution of star exists in E, we say that capital E avoids star. Okay. Now, of course, you will realize that there is nothing sacred about just this equation, x plus y equals to z. This concept of containing non-trivial solutions or avoiding solutions, it's far more general. So why don't I give you maybe the slightly more general definition, and we'll keep that in mind. So maybe more generally, what we look at is an equation of the following form: a1x1 plus a2x2 plus apxb equal to 0. And p, the number of unknowns, is always larger than or equal to 3. x1, x2, xp are the unknowns. And the coefficients, a1 through ap, these are fixed. These are the coefficients. And in general, we can pick them to be anything in R or Z. And we are going to make one further restriction, namely that all the coefficients add up to 0. Otherwise, I'll explain to you in a moment that this is just to avoid trivial situations. So this is our assumption. That A1 summed all the way up to AP is 0. When we have such an equation, we call such an equation a translation invariant linear equation. So if we have an equation like double star, and following this assumption A, star, double star with A, is called a translation invariant linear equation. Why translation invariant? Well, because this assumption capital A simply means that if x1 through xp obeys double star, then if you shift each entry by a fixed amount, so let's say t, also obeys double star. And that's because of the assumption A. Okay. So, of course, the x plus y equal to 2z is a special case of double star. And something that I should have also mentioned is that x plus y equals 2z, not only is it a translation invariant linear equation, it also has a very clear geometric significance, which often drives these kinds of problems, that what it depicts is the existence of 3 equally spaced points. In other words, x, y, and z are 3 terms of an arithmetic progression. So this is just another way of saying that x, y, z are 3 terms of an arithmetic progression. Okay, so with these definitions in place, the question that we are going to try and understand is the following. So here's maybe the revised question. What can we say? So when does a set E contain or avoid non-trivial solutions of an equation of the form double star? In particular, if you go back to our prototype example, x plus y equal to z, for example, can one find a set capital E large enough, whatever that means, without any non-trivial solution of x plus y equal to t to z, in other words, without any non-trivial 3-term arithmetic progression? Because we just made the case that x plus y equal to 2z on the real line has tons and tons of solutions. But can one find these kinds of sets where 3-term arithmetic progressions are absent? So this is the kind of question, or just the flip side of it is any large E forced to contain a 3AP? So these are some of the prototypical questions that's going to drive our talk today. So I'm going to stop for a moment and see if there are any questions so far.
I don't see any question except TSS said if you could turn your video on, but I already told him there is a little problem there.
So let me see. You see what's going to happen. I'm going to try, if I let me see, where am I? The trouble with turning my video on would be that you may not see anything except my ceiling here. Do you see?
Yeah, exactly. You're right.
Yeah,
We
it's
can
exactly
see the same thing. Yeah.
Okay.
Yeah, this
All
is
right.
not very helpful.
Yeah.
Okay, this is because I'm writing on a tablet, so it just faces right up. Okay. All right. So this is, by the way, if you don't have any questions for me, I have a question for you. So at this point, I have, I think what I have done so far is posed a sort of set of questions to you. Usually, and this question is for the students in the audience, what happens when somebody poses a problem that they are interested in pursuing? You have to ask a question right back. What is the question you should ask?
I'm thinking that what kind of state can done the job. I'm just
Sorry, I
restricting
can't
my
hear anything. Do you want to speak up a little?
ma'am, Sudesh ma'am. Can you mute
Yes.
it?
Can you speak a little bit louder? I can mute myself, yes.
Yes. Can some ma'am actually my question is can the Bounded set done the job. E is
Can
bounded some.
would a bounded set have done the job? What do you meaning done the job in terms of what?
Solution. There is exist a solution of your equation.
Well, not every bounded set is going to contain a solution of this equation. It's a good question. So let me write down what you just said, and it's a nice discussion. Why don't we do this? So the question is, so your response is, does a bounded E contain a solution? And so if we think about it a little bit, then we will see that just bounded is not going to work because, well, why? Let's say we have 0, 1, and 10. And I think Archana had the similar questions, and I think she asked, is E discrete? Well, here is an example of a set. This is bounded. So this is definitely bounded. It's also discrete. And there is no 3-term AP. These terms are not an arithmetic progression. So bounded alone is not enough to guarantee solutions. So let me go back then to my question back to you. So we are trying to determine whether a set E, under what circumstances will it contain or not an equation and a solution of a translation invariant linear system. And I am actually not asking for any answers from you. I'm asking for questions as to what if you were asked to explore a question in this area. Oh, yeah. Unfortunately, the person who answered this question is not a student, but my professor. But well, I'll take it. So Professor SMS said, why did you ask this question? Is it just a mathematical challenge? Or are there actual real world applications for questions like this? Why should we care? So let's take that. So this is sort of a request to all of you students out there. Don't ever let oldies like me tell you what to do. You should always push back saying, why? Why is this a line of inquiry worth pursuing? So let me try to say a few words about why we should care. So why do we care? Now, there are several reasons this line of research has remained really vibrant and active for many years, and it has a tremendously rich heritage. So it comes from, maybe I'll start with the modern applications first. You see, this line of genre of problems, it's falls under the premise of an area called pattern recognition. Now, this is an extremely vast subject, and I'm not going to try to make the case that the problems that we are talking about today are, it's probably a very, very tiny part of this immense field called pattern recognition. So pattern recognition, you'll probably realize that this shows up a lot in medical imaging, in oil exploration and seismic imaging, in analyzing massive data sets where people have a humongous data cloud in which they are trying to determine some kind of configuration. Now, these sorts of pattern recognition questions can be handled in several different ways. Sometimes, so the generic question is this: suppose E is a set and capital P is a pattern. And you can pick your favorite pattern. This could be a geometric pattern, an algebraic pattern, an analytic pattern. The question is, does E contain, so for example, let's say this set is in R2 on the plane. Let's say this is a pattern. For example, a pattern could be, let's say, an equilateral triangle. I'm just trying to give you simple examples here, but of course you can make it as complex as you want. Does E contain an affine copy of this P? So okay. Now, oftentimes one can try to do this by an exhaustive search. So that's a brute force method. So if you have a finite set E, you just look for all triples of points and check if they are the vertices of an equilateral triangle. But first of all, that's not really a very elegant solution. It's extremely demanding in terms of time and computing power. And second, if capital E happens to be infinite, then an exhaustive search is a non-starter. So what we would like are some theoretically sound reasonings that will ensure that a pattern P exists in the set A. And what I was talking about today with the progressions is a very simple, maybe the starting example of this line of inquiry. Okay. What's the other reason? These kinds of questions have a lot of applications in number theory. And this is especially true when the ambient space is discrete, namely the space of integers. So especially when the ambient space is Z. And I'm going to say a few words about this in a moment because we'll start talking about examples and non-examples. So I'm going to say that this is to be continued shortly. And third, in the continuum setting, questions of this type are related to notions of size. So I'm going to say that this also interfaces with this area that I love called geometric measure theory. Okay, and I'll tell you what exactly this does. And it's related to, these kinds of questions are related to notions of size. And let me explain. Okay, what do I mean by notions of size? So this goes back to some natural intuition. So when we ask this question, suppose that E is a set, and so let's say here, we say E is a set and P is a pattern. Does E contain a copy of P? Well, somebody could say, well, not, of course not. Because let's say if E has just one point and P is an equilateral triangle, there is no way that E is going to contain a copy of P. And if E is the empty set, it doesn't contain a copy of anything. So what are we talking about? Well, that's where the notion of size comes in. So intuition says that small sets, and I realize that the word small is not really quantitative. I'll put it in, so small or sparse sets should not contain many patterns. That's our many patterns, but large ones should. Because the more points, the more elements you stuff into your set, the chances of your intended configuration or your intended pattern showing up in that set increases. So that seems to be the intuition. But of course, the devil is in the details. What do I mean by small? What do I mean by sparse? And what do I mean by large? And it turns out that there are many competing definitions of size. And depending on how you measure largeness, this intuition could be true or this intuition could be false. And this discussion of the notion, quantification of size has led to a rich analysis of the structure of sets. That's another reason for trying to understand this line of questions. Okay, so in the rest of the talk, what I'm going to do, I'm going to talk about some examples and non-examples of existence of patterns, and I'll keep like the 3-term arithmetic progressions as our touchstone example. Okay, so let's start in the discrete setting. Okay, all right. So I have to tell you this. This is one of the, maybe there, if there is one takeaway result that you should from this talk, it's this theorem of Roth generalized to this theorem of Zemuredi. So I'm going to sort of state this as Roth's theorem. So what does it say? It says that suppose you have a set capital E, subset of the natural numbers. So natural numbers meaning all the positive integers, 1, 2, 3, etc. Okay. And suppose that E has positive asymptotic density. Okay. All right. So what does that mean? That means that if you look at E and you see how many of the first capital N natural numbers belong to E. So you are looking at the cardinality of the set E intersected with 1 through N. And then you look at the proportion by dividing by N. And you take the lim sup of this fraction as capital N goes through infinity. So this is by definition the positive asymptotic density. I'm sorry, this is by definition the asymptotic density, and I'm going to assume that that's positive. So suppose E has positive asymptotic density, then the conclusion of Roth's theorem says, then E contains a non-trivial 3-term arithmetic progression. In other words, a non-trivial solution of x plus y equal to 2z. Okay, so this is one of the sort of landmark results in not just in number theory, but also in additive combinatorics. This was strengthened by André Zemuredi Same assumption, same positive asymptotic density. But now, for every k, Zemiredi says that you choose any k larger than or equal to 3, and E contains a k-term arithmetic progression. So arbitrarily long arithmetic progressions. About 10 years ago, there was a big, by the way, many of you know, I'm sure, that Andrei Zemiredi, maybe 3 or 4 years ago, won the Abel Prize. And even among his many fundamental contributions, the Swedish Academy of Sciences singled out this one theorem as one of his most substantial accomplishments. So about 10 years ago now, there was a result that was that made a really good big splash, which is, you remember, this was this result of Green and Tao, where they proved the existence of three-term arbitrarily long arithmetic progressions in the primes. So I want to sort of keep these results up here and say a little bit about what they mean. I said just a little while ago that there are these notions of size, that small sets should not contain patterns, large sets should. And these results, well, the results of Roth and Zemiredi support this intuition. The notion that a set E has positive asymptotic density, this is the quantification of the size of the set E. So this says that the set E is large. So this is a quantification of the size of E. And here, E contains a non-trivial three-term arithmetic progression. This is the existence of a pattern.
Malabika, I'm just interrupting you because SMS has a question.
Yes.
Yeah, let me read it out. SMS is asking, what is the asymptotic density of primes?
Exactly. Thank you. Just I'm getting there. Okay. So the asymptotic density of primes is 0. So this follows from the prime number theorem, which says that, which is the reason why this result was such a big one. So primes have asymptotic density 1 over log n, and that's, as n goes to infinity, that's 0. So it certainly does not fall within the scope of Zemiredi's theorem. Nonetheless, even though these primes are sparse, it's a small set. However, it still contains arbitrarily long arithmetic progressions, which on the face of it seems counterintuitive, and which makes this result all the more spectacular. Does that answer your question, SMS?
Yes, it does. You said that it uses prime number theorem, so I will see it later.
Sorry, say that again.
Yeah, it answers my question, but you also made the statement that it can be proved using prime number theorem.
Yes.
Okay.
Just this statement. Yes.
Pardon?
So I think, just the statement that it has asymptotic density 0 can be used, proved using the prime number theorem.
Yeah, that's all right. Yeah. So that yes. I will check later.
Okay. Hello, ma'am.
Yes.
Ma'am, you told about existence of APs. So,
yes.
I mean, say for k-length AP, the difference will be same for any k-length AP, or as k varies, so the difference between two terms in the APs that may differ.
You mean for a k? So are you asking about the definition of a k-term AP?
No, ma'am. I'm saying that, I mean, here you have given the, I mean, these theorems are giving existence of APs, right? So what is the
Yes.
difference in two terms in the APs?
That is not known. So the statements like this, they do not say anything about the size of the common difference of the APs. And it is in
Yes.
fact even more important to notice in the case of all of these statements that it doesn't say that I am giving you, let's say, a common difference of 10. Does my set capital E contain a copy of a progression where the common difference is 10? Such a statement, these are not such statements. These are statements just about k points being equally spaced. The results of the type that you are asking, where statements can be made about the common difference, those also exist, but these are not that kind because, for example, if you have a bounded set or even a bounded interval, let's say -1 to 1, it will contain many APs, as many APs as you want, but it cannot contain any arithmetic progression with common difference 100. So the question has to be formulated in a particular way that is meaningful for the set at hand.
Yes, ma'am. It's fine.
Okay, all right. Okay, great. So I'll keep moving. So this one is very counterintuitive. The first one is not. And here's an example. This is an old example of Beren. And maybe if there is one proof that I want to share with you today, it's going to be this one. So let me talk about another counterexample, a counterexample of Beren. So it shows why the positive asymptotic density condition is necessary in Zemmeredi's theorem. So a counterexample of Beret. Okay. So what is
Malabika, sorry, I'm interrupting because Priya Rao writes, for using the theorem, we have to know about set E, which is our first M. So
Yes.
how can we use the theorem?
How can we use this theorem?
Priya, maybe you can explain.
Hello.
Yes.
Ma'am, for asymptotic density,
Yes.
we have to find the cardinality of E intersection the set of natural numbers.
Yes.
So for that we have to find first E.
Yes.
And first the first question which you have right was how to find the E which will give non-trivial solution like that.
Mm-hmm.
So the set E you have
Yes.
defined.
Yes.
That is our aim to find, means our aim is to find E. But we are going to take the cardinality of E intersection the set of natural numbers.
Yes.
So nothing is known, then how can we find any result?
Well, no, I think you see, this is a statement. It's up to you to find out this set E that will obey this property. For example, let's take some simple cases, okay? Let's say capital E is the set of odd numbers. If capital E is the set of odd numbers, do a quick check and say, let's say, for example, let's write some stuff down. Say if E is odd, then this asymptotic density is half. If E is even, the asymptotic density is still half. For example, if you choose, let's say, capital E a random set, so let's say you keep picking this set E, choose randomly. So what does that mean? That means that every time, let's say you look at 1, you toss a coin. If the coin falls heads, you pick the point 1, otherwise you pass. Then you go to the next point, you toss a coin. If it falls heads, you pick it, otherwise you pass. That's a random set. And you can check that random set also has asymptotic density 1/2. So The Roth's theorem gives you a sufficient condition for E to contain a non-trivial three-term arithmetic progression. The challenge is up to you to figure out. There are plenty of sets capital E that you can think about which obeys this property. And it's up to us to verify this condition for those sets. So I gave you right now the odd and the even, or capital E, which is, let's say, 1 mod n, and sets that are randomly chosen with a certain probability. These are all examples of E which will obey the condition of Roth and Zemmereri's theorem. Does that answer your question, Priya?
Hello. Yes, ma'am.
Okay, good. All right, so let's continue with this example of Berendt. So here's a set E. So what he said is that suppose, so there exists a set capital E, n. So for every capital N sufficiently large, there exists a set En between 0 to n minus 1 with the following properties, such that the cardinality of En is large, so it's a very large set, and I'll explain how large. So it's larger than n times e to the power of minus a constant times square root of log n, and En contains no three-term AP. Okay, so this is this example of Berendt, and this is it's very counterintuitive. So it says that the set E is large, and this is no pattern, that not, at least not the pattern that we are looking for. So how does this proof go? And I wanted to tell you this proof because even though this is an old result, the proof is, I still think it's a stroke of genius. This is how Berendt goes about proving this. So he says that we are going to pick E sub n in the following way. These are going to be integers to some base d. So these are points, these are integers x, and j goes from 0 to n minus 1. Capital N here is d to the power of n. So you are expanding all the integers between 0 and n minus 1 with respect to base d, and the xj's are the digits of that expansion. So typically, each xj will have to go from 0 to d minus 1, but I am only going to let them go up to d over 3 for my set. And here's the important part. I want these digits to lie on a square, or I'm sorry, on a sphere. So x1 square plus x2 square plus x n minus 1 square is equal to some capital R. And this capital R goes into the definition of En. Okay, so what Berendt says is that there exists such a capital R for which the results of his theorem are satisfied. And how does he prove this? This is the best part of all. He claims that no set ER contains a three-term AP. And why does he say that? So he says that we have taken this x and we have identified up x with its row of digits, x0 through xn minus 1. And these digits, they lie on a sphere of radius square root of r.
So SMS has a question. Can D be anything?
Say that again.
So SMS, your question is, can D be anything? Any
D
D?
is any large integer. So you can choose D to be larger than or equal to, let's say, 3, and that will work.
Oh, so any D greater than or equal to 3 will work.
Yes.
Okay.
Okay. And now, so let's say we have a point here, which is x, which is the vector x of x0 through xn minus 1. And the claim is that there are no APs, because if you take another point y, and an arithmetic progression has to mean that the point z lies strictly in the midpoint between x and y. And if x and y lie on the sphere and the sphere is strictly convex, this z cannot lie on the sphere. So that shows that no matter what capital R is, this En cannot contain a 3-term arithmetic progression. Okay. Now, what about the size of En? Well, now let's go back to that. Notice what are the possible choices of capital R. So note that R can take at most n times d over 3 to the power of square many values, because that's the largest that each xj can be. However, if these sets are all disjoint in R, and if you look at the cardinality of their union, it covers all the digits which are between 0 and d over 3. So that's the same as d over 3 raised to the power of n. Okay. So now do a pigeonholing. If the total size of this is this much and the possible choices of capital R are that much, then there must exist. So that means from here, there must exist an R. So this is the pigeonhole principle, such that the cardinality of En of R is greater than or equal to n the maximum d over 3 to the power of n minus 1 and divided by the total number. So I'm sorry, I got this all wrong. So d over 3 to the power of n divided by n times d over 3 square. So this is greater than or equal to 1 over n and d over 3 to the power of n minus 2. So now I'll let you figure out that if capital N is d over 3, d to the power of n, that this is greater than capital N times e to the power of minus constant times log n. So this is a large set. So this sort of ties nicely patterns with a geometry of the set. So let me see. So Deshna, how much time do I have left?
Well, we have 1 hour talk, but we are really engrossed. So please continue.
So why don't I do something? I'll sort of gently wind down, and then I'll keep some time for the questions and answers. Okay.
Okay.
So what I talked about today is just in the discrete setting, something about the existence and non-existence of patterns in the simple setting of arithmetic progressions. There is a really humongous literature out there about patterns in the continuum. So this is one of the areas that I have been working on in R, and it's surprising how the notions of patterns the discrete and the continuum analogs feed off of each other. And the patterns in R, they bring a basket of own issues themselves. And there are these notions of various sizes, like notions called of dimension. So if a set has, let's say, a certain kind of Hausdorff dimension or Minkowski dimension or Fourier dimension, then certain patterns exist in such sets or don't. So there is a huge literature out there. So Hausdorff, Minkowski, Fourier, and just as we talked today about Zemmeredi's theorem and Berend's example, there are similar examples and counterexamples with these notions of dimensionality. And they interface a lot, not just with geometric measure theory, but also dynamical systems and ergodic theory. And this is a vibrant research area unto itself. So I won't say much more about this, right, because I really do want to keep some time for questions and answers. So thanks again for listening, and I'll wait for your questions.
So let us first thank the speaker. Wonderful. We are all engrossed.
Malabika, can you go back the last two?
Sorry, SMS, did you say something?
Yeah, I asked Malabika to go back to the last two. Berend's non-example.
Berend's non-example? Okay, hang on.
Yeah. Can we have full screen, please? Can we have full screen, please? Yeah.
Yes.
So the points are these points. Summation j equal to 0 to n minus 1.
Yes.
J dn minus 1. Huh? Little bit below.
Okay.
Where no. I mean up. Yeah, here. And this is on the sphere.
Yes.
Okay. So how does event? I missed the point here. So
your question
it does not
is
contain 3-term AP. I missed the point.
Okay. So
because
why does it not contain?
How is this thing that coefficients are on the sphere?
Yes.
But you have to show that such x's are not in. There are no 3 such x's in AP.
Yes. Okay. So let's go over this carefully.
Yeah.
So,
please.
okay. So suppose that, so remember that we are looking at En of R, and En of R is by definition this set where it has this summation xj d to the power of j, and I'll just for the say j from 1 to little n for now, not that it matters, and 0 less than or equal to xj less than d over 3, and summation xj square is equal to r. Okay. Now, suppose this set contains a non-trivial 3-term AP. So suppose it contains a 3-term AP x, y, and z, which means that we must have.
Why don't you write xzy? Why don't you write xzy?
Okay, so let's say this is x, z, and y. So which means that we will have x plus y equal to 2z. Okay, which means if I write down that this is my x, so if I put this together, what I will get is j summation j from 1 to n xj plus yj d to the power of j. This is equal to the sum of 2zj d to the power of j. With me so far? Okay.
Yes, I am with you.
Yes, good. So now look at these coefficients and this digit. So this digit
is less than 2d/3 because of this condition, right? Xj and Yj, they are both in E sub n of R. And this digit is less than 2d/3 as well. Now remember that the digit expansion of any integer with respect to a fixed base d is unique. So digit expansion is unique. Which means that digit by digit, each one of these, which means that xj plus yj has to be equal to 2zj for every j.
Yeah, I got it now.
Okay, good. And then that was the picture that I drew here. This is the
I got
xj.
it.
This
Yeah.
Okay, excellent.
Yeah, I got it.
Thank you.
Nishant, if you want, you can ask your question. Since this time is for question answers. Nishant, I think, had something in the chat box, but if you want, you can ask your question.
So my question is the following. I often hear that there's a difference between 3-term arithmetic progressions and 4-term arithmetic progressions, and you also sort of emphasized on 3-term progressions throughout your talk. Is one of the reasons that 3-term progressions have this single equation x plus y is equal to 2z, while 4-term arithmetic progressions would require 2 equations to describe them? Is this one of the, I'm sure that there are deeper reasons for the difference, but is this one of the reasons?
Well, yes, yes and no. So it is definitely true that if you were to write a 4-term arithmetic progression in terms of a linear equation, then you would need 2 equations in 4 variables to represent it. But I think maybe the deeper reason that goes behind this distinction between 3-term APs and 4-term APs is because often in practice, whether it's in the discrete setting or whether it's in the continuum setting, certain techniques that for proving existence of 3-term arithmetic progressions simply fail or are known to be not true for 4-term arithmetic progressions. And that does not really go back to how many equations we need to represent it. It goes back to the fact that a 4-term arithmetic progression is an affine copy of 4 equally spaced points. So a 4-term arithmetic progression you can think of as being an affine copy of 0, 1, 2, 3. And when you have the more points you have in your pattern, the problem gets harder. So I think the deeper issue here is that whether you look at Zemiridis theorem being more difficult than Roth, whether you look at even in the continuum setting, proving the existence of 4-term arithmetic progressions in certain sparse sets is still an open question. It goes back to certain techniques that we currently have being insufficient. Fourier analysis, for example, is sufficient to handle 3-term arithmetic progressions, but is known to not be sufficient for 4-term arithmetic progressions. One of the reasons Tim Gowers' proof of Zemiridis theorem was so important was because he introduced these notions of the UK norms, the uniformity norms, and the U3 norm is the same as it uses the Fourier coefficients, but the higher order Gowers norms like UN, which are used to determine the existence of 4-term progressions or 5-term progressions, they are significantly stronger. So technologically, it's more challenging.
Thank you very much.
Any other questions, Stefan?
Yes, First of all, I would like to thank you for the talk about a really fascinating, rich topic. I would like to add one comment. So there's a conjecture of Erdős, which says the following: if one is a subset of n, then it is ensured that it is an arithmetic progression of arbitrary length if the sum of the reciprocals tends to infinity. That's quite a fascinating conjecture, because if it is true, it actually implies the green Tau theorem, because for the primes it's the case that the reciprocals sum up to infinity.
Yes.
And there seems to be there is a recent paper which claims a proof for three-term progressions of that Erdős conjecture in 2020.
Who is it by?
By Bloom and Cisak.
Okay. Okay.
Something very interesting.
Yes, since you mentioned Erdős, there is this another extremely famous problem, also due to Erdős and also involving patterns called the Erdős similarity problem, which still is open. It says that there can be no infinite set or no pattern consisting of infinitely many points such that a set of every set of positive Lebesgue measure contains an affine copy of it. So this is known to be true for finite sets. That's again a very old classical result of Steinhaus. But the fact that it is true only for finite sets and cannot be true for any infinite set is another conjecture of Erdős. It's notorious in the field and still no proof.
I see.
Sorry, can you repeat this question again?
Yes, let me write it down. Say that again?
Sure. Yeah, please go ahead.
Okay, so let me write down the question. So it's called, so every time I want to feel frustrated, I go back to this question. So this is called the Erdős similarity problem. And say that A is any infinite set. Show that there exists a set E, subset of R, such that the Lebesgue measure of E is positive and E does not contain any affine copy of A. So that means what does that mean? i.e., there does not exist any x comma t with x in R and t non-zero such that x plus ta is contained in E. That's the Erdős similarity problem. And it's known that this is known to be true for certain infinite sets, but the issue is to show it for every infinite sets. And if you wanted to look at an example which would be great, like a great progress, for example, even for A to be in the geometric sequence 2 to the minus n, this is unknown.
Did you say about the finite E?
Yes.
No, finite A?
Yes, so that's an old result of Steinhaus. So this is known for, so this is Steinhaus's theorem. So for every A finite and any E subset of R, in fact, this is also true in Rn, but this is with positive Lebesgue measure. There exists X in R and T non-zero such that X plus TA is contained in E. So this is known. And this follows from the Lebesgue density theorem.
So the A that you chose was 2 to the power minus n. So if it is uniformly discrete, is it easy? So if the distances are, say, of course, for natural numbers, it's very easy probably to construct such a set E, but
yes. So the real challenge here is if your set capital A is unbounded, and if you take any discrete set which has a minimal separation, it will be very easy to prove this. All you have to do is choose a bounded set E of positive Lebesgue measure. But the real challenge is when you have a set capital A with a limit point, so a sequence that converges to 0. So for the A's for which these are known are, for example, sets that decay arbitrarily, like slowly, like 1 over n. So this kind of set A is known. There are some other sort of old results by Koulontzakis and Bourgain. So they have certain subsets like 2 to the power minus n to the alpha added with itself. These kinds of sets are also known. But even this simple one remains open. So when you look at this example, to make it for it to be meaningful, choose capital A to be a bounded sequence with a limit point.
Thank you.
I have another question. So you mentioned already results in the setting of real numbers. Is there some analog of Roth's theorem in terms of the Hausdorff dimension? So if Hausdorff dimension is greater so and so, then we have a three-term progression. Is there something like that?
Yes. So there is an analog of Roth's theorem, and there is an analog of Berend's counterexample. So let me see if I can say a few words about that. Okay. So in the real line, this example, this result that I said of Steinhaus, this is the analog of Roth's theorem in R. So this is the analog of Roth, and I'll explain why. If you pick, let's say, capital A to be -1, 0, 1, okay, so this is my finite set, and you suppose also this condition, E positive, this is the analog of positive asymptotic density. Remember that there was an assumption of positive asymptotic density for in the integers. This is our continuum analog for that. And then Steinhaus's theorem says that this is contained in E, which means that x minus t, x, and x plus t is contained inside of E. And this is my three-term AP. Okay. Now, so this is the analog of Roth. There is also an analog of Behrend. So what is the analog of Behrend? That there exists a E subset of R, Lebesgue measure 0, but the full dimension, Hausdorff dimension 1, and E contains no three-term AP. And that's the analog of Behrend in R.
Okay,
Which
thank
of
you.
these results are yours?
Yes, SMS, what did you say?
Which of these results are yours?
None of them, because these are our, so there is, maybe I should tell you about what is the kind of results that I have been talking about. So I'll be brief. So let me, so what I have been, because these are known, what I have been trying to understand is with Hausdorff dimension being 1, it seems that it is easy to have, even though the Hausdorff dimension is large and the set is large in that sense, it is not sufficient to contain non-trivial solutions of a translation invariant linear equation. So something that I have been trying to study is what should I replace this by? Can I replace by a stronger condition, by a stronger size requirement? So that every time the size is large, it cannot have a result like this. So E has to contain So over the last 10 years or so with different co-authors, Isabella Laba, Rob Fraser, Yu Liang, what I've been doing is trying to systematically study this notion of size and the existence of pattern relative to that notion of size. And I didn't get a chance to talk about that today, but maybe next time.
Absolutely. We'll wait for it.
Hello, ma'am. How much background one needs to work in this thing? Because your talk was very wonderful and very simple, at least main talk. So it doesn't look like we are requiring too much background study of major theory or ergodic theory. What is that? So could you please
Actually,
brief and
that's a
some
very good
differences?
question, Devendra. So I mean, the appeal of this area is that the questions are simple to state. But I don't want to mislead you by saying that the methodology is equally simple. If you just have to look at maybe just the green tau result, which is at this point more than 10 years old, and you will realize that as simple and elegant the statement might be, the proof of it, and more importantly, the ideas that are hidden in the proof are truly deep and profound. So there is a lot of measured theoretic machinery, a lot of machinery from ergodic theory, additive combinatorics, a lot of, sometimes depending on what kind of problems you are working on, Fourier integrals and Fourier integral operators. There is a huge arsenal of tools that go into this field. I, of course, tried to keep things simple for this talk because I wanted to make it appealing and meaningful for a young audience. But if you want to dig deep into this literature, you will need mastery of a few different things.
Yeah, so would be a related question like you are expressed in the talk that what kind of question people ask and what kind of mathematical challenge and if it has application or not. So how a young student, when a professor like you talks about a subject or what is called advertises a subject, how a student should decide about that topic? Means what could be the parameter to follow a question or follow a discipline? A general kind of question, and maybe you have some thought of methodology.
I cannot guide you on that, Devendra, because it's about how much when somebody looks at anything, whether it's an artistic performance, whether it's a movie, it's a piece of art, it moves people in different ways. And some people want to observe and are happy. Some people are probably much more inspired and they want to pursue that avenue in greater depth. Of course, if you commit to any direction, that no matter what direction you choose, there is always this expectation that there will be an investment of effort in some level. There is no shortcut, there is no simple way. But this is just, these talks, like mathematical talks, are just meant to give the audience a flavor of the different types of math that are being pursued in this world. You should sample a wide range and then choose the one that appeals to you the most.
Okay, thanks. Thanks for a nice talk and intriguing title of this talk.
Any other questions, anyone?
Is there another talk coming up soon on a similar platform on Zoom? Perhaps.
If the talks and slide would be posted somewhere on the web or like YouTube?
Yeah, I am recording it, so I will. We have a channel, Department of Mathematics at RKMVERI, so I'm going to upload it there.
Thanks.
Yeah, I would find it very nice if you could give another talk at some point about the setting in the real number and your results in this direction.
Yes.
Thank you. Thanks,
Yeah.
everyone. I'll
Yeah.
leave now. Thanks again, Sudeshna, for the invitation. It was a pleasure. Bye now.
It is our pleasure, and we are eternally grateful to you. Please give Malabika a big hand again.
Thank you. It was great seeing you all. Bye now.
Great. Thank you so much, Malabika. Okay, yeah, somebody had asked a question about the YouTube channel. The name of the channel is RKMVERI Math. Okay, somebody asked, so. Yeah, she has left.
Okay, Sudeshna, bye.
Yes, bye SMS. Thank you everyone who joined.
Yeah,
And
very lovely talk.
yeah, it was really engaging. And Stefan, if when will be the next talk? I think next week we don't have anything.
And no, after November, on 22nd, it will be on.
Okay.
Giving his talk.
Okay.
Yeah.
Bye everyone.
Yeah. Then
everyone
bye
have a nice pujo. Yeah. Thank you. Bye.
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 Bye. Okay, I need to first stop recording.